Section 1. In the summer of 1940, the survival of Western democracy hinged on a simple, terrifying inequality. Intelligence estimates suggested that for every fighter plane Great Britain could launch, the German war machine could launch 4. The Luftwaffe was an unstoppable tactical juggernaut that had just rolled across Europe, and the mathematical models predicted total British collapse in less than 6 weeks. This was not merely a question of courage. It was a calculation of deficit. Now, let's open the operational records and analyze the systems that defined this campaign. The strategic context of July 1940 presents a scenario of absolute isolation. France had fallen, removing Britain's continental buffer and leaving the English Channel as the sole geographic barrier against the Wehrmacht. However, a naval invasion codenamed Operation Sea Lion by the German High Command was logistically impossible without one critical precondition: absolute air superiority. As long as the Royal Air Force remained operational, the German invasion fleet would be vulnerable to catastrophic destruction before reaching the Kentish coast. Therefore, the German objective was clear, linear, and brutal: destroy the RAF Fighter Command. This was to be achieved by bombing airfields, destroying infrastructure, and engaging British fighters in a war of attrition that the numbers suggested Britain could not win. When we analyze the opposing forces through a systems lens, the disparity is staggering. The Luftwaffe operated as a tactical air force designed to support ground blitzkrieg operations, boasting nearly 2,600 aircraft ready for the assault, including roughly 1,200 fighters and massive fleets of medium bombers. Across the Channel, Air Chief Marshal Hugh Dowding could muster roughly 700 serviceable fighters, primarily Hurricanes and Spitfires. Conventionally, military history focuses on the pilots, the few, and the dogfights above the White Cliffs of Dover. But from a logistical perspective, this battle was a clash of industrial outputs and resource management. The core problem for Britain was not simply winning individual engagements. It was managing a high-velocity system of supply and demand under direct fire. The demand was the daily consumption of aircraft and pilots due to combat losses and accidents. The supply was the nation's industrial capacity to manufacture airframes, and the training command's ability to generate competent airmen. If the rate of attrition exceeded the rate of replacement for even a few weeks, the system would enter a death spiral from which recovery would be impossible. The Luftwaffe believed they could force this collapse by overwhelming the British defensive capacity. They viewed the RAF as a static inventory to be depleted. However, they failed to account for the elasticity of the British supply chain and the sophistication of the command structure managing it. The battle would not be decided by who had the most planes on day one, but by whose system could sustain the highest tempo of destruction without breaking. Section 2. To counteract the staggering numerical deficit, Air Chief Marshal Hugh Dowding did not rely solely on the bravery of his pilots or the performance of the Spitfire. Instead, he engineered the world's first fully integrated air defense system, a complex logistical network designed to manage information as effectively as it managed ammunition. When we map the architecture of what became known as the Dowding system, we see a prototype of modern network-centric warfare. The plan was not to meet the Luftwaffe force on force in a chaotic brawl, but to execute a strategy of extreme resource conservation and precision allocation. The operational goal was simple: strictly ration the engagement. The RAF could not afford to maintain standing patrols flying aimlessly hoping to spot the enemy, as this burned fuel, fatigued pilots, and increased engine wear without guaranteeing combat contact. Dowding needed a just-in-time delivery system for air power. He needed to vector specific squadrons to specific coordinates at the precise moment required to intercept, and not a minute sooner. This system relied on a 4-tiered supply chain of information. It began at the periphery with the chain-home radar network. These towering steel masts acted as the early warning sensors, detecting inbound formations as they formed up over France. However, raw radar data is messy and often inaccurate. To refine this input, the system utilized the Royal Observer Corps, thousands of human spotters equipped with binoculars and field telephones who tracked inland movements, verifying altitude and numbers. This raw data flowed via dedicated landlines, the nervous system of the defense, into the filter room at Bentley Priory. Here, we see the system's true genius. In an era before digital computing, the filter room acted as a biological CPU. WAAF, Women's Auxiliary Air Force, Personnel processed conflicting reports, triangulated positions, and distilled the chaos of war into a single verified operational picture. This clean data was then pushed down to group and sector HQs, where controllers scrambled squadrons with mathematical precision. The logistical impact of this information architecture cannot be overstated. It functioned as a massive force multiplier. Because the RAF knew exactly where the enemy was, they could keep their fighters on the ground, refueling and rearming, until the enemy was within range. This meant that a single squadron of 12 Hurricanes could do the work of 3 or 4 patrolling squadrons. They were essentially stored inventory that could be deployed instantly. Conversely, the Luftwaffe plan was structurally flawed because it lacked this feedback loop. German intelligence underestimated the sophistication of the British radar network, believing the towers were isolated stations rather than nodes in a unified grid. Consequently, German fighters, escorting their bombers, were forced to operate on a tether. They burned precious fuel waiting for form-ups and searching for targets, often arriving over London with only 10 minutes of combat fuel remaining. The British plan, therefore, was a triumph of efficiency over volume. By controlling the information space, Dowding ensured that the RAF did not have to defeat the entire Luftwaffe every day. They only had to defeat the specific raid attacking a specific sector, applying maximum force at the critical bottleneck. The defense was designed to bend, absorbing the blows through a resilient communications web, ensuring that while airfields might be bombed, the system's brain and its ability to direct the flow of battle remained intact. Section 3. While the Dowding system managed the distribution of air power, the foundation of the defense rested entirely on the availability of the hardware itself. In May 1940, the outlook was bleak. The RAF had left hundreds of serviceable aircraft on the airfields of France during the retreat, and domestic production was strangled by peacetime bureaucracy. The prevailing narrative suggests that the RAF was constantly on the verge of running out of aircraft, fighting with a dwindling inventory. However, when we drill down into the Ministry of Aircraft Production's records from that summer, we find a counterintuitive reality. The supply of fighter aircraft actually increased as the battle intensified. This was not an accident. It was the result of a radical restructuring of the industrial supply chain. The catalyst for this industrial pivot was Lord Beaverbrook, a newspaper tycoon appointed by Churchill to run the newly formed Ministry of Aircraft Production. Beaverbrook was not a logistician by trade. He was a disruptor. He recognized that the existing supply chain was optimized for long-term sustainability and perfect accounting, not for immediate survival. He immediately dismantled the hierarchy of methodical production. He cut across the rigid prioritization schedules, commandeered raw materials intended for bombers and naval vessels, and funneled them exclusively into 5 key aircraft types, with the Spitfire and Hurricane taking absolute precedence. In supply chain terms, he sacrificed product diversity and long-term capacity for immediate throughput. But the true enabler of this victory, the hidden system that arguably saved the RAF, was not the factories building new planes. It was an organization that operated in the shadows of the manufacturing giants. The Civilian Repair Organization, CRO. When we analyze the life cycle of a fighter aircraft in 1940, we see that a plane lost in combat over England was rarely a total write-off. Unlike the Luftwaffe, whose downed aircraft were lost permanently behind enemy lines, the RAF was fighting over its own territory. This geographic advantage allowed the CRO to turn the English countryside into a massive, decentralized recycling facility. The CRO system functioned as a reverse logistics network. When a Hurricane crash-landed in a Kentish field, it wasn't just scrap metal, it was a repository of high-value components. Specialized recovery teams, often working while air raids were still in progress, would winch the wreckage onto Queen Mary low-loader trailers. These carcasses weren't sent back to the primary Supermarine or Hawker factories, which were already operating at maximum capacity building new airframes. Instead, they were diverted to a sprawling network of civilian contractors, garages, bus depots, railway workshops, and even furniture manufacturers that had been hastily retooled for aerospace repair. This distributed network provided immense resilience. If the Luftwaffe bombed the main Supermarine factory at Woolston, which they did, causing significant damage, the repair network remained untouched. It was too granular, too spread out to be targeted. Inside these makeshift workshops, wings were patched, fuselages straightened, and Rolls-Royce Merlin engines were stripped and rebuilt. The logistical genius here lies in the concept of cannibalization. The CRO created a circular economy of war material. A Spitfire with a shattered wing might be mated with the fuselage of another Spitfire that had suffered engine failure. Parts were standardized and swapped with a speed that defied peacetime engineering protocols. The data highlights the magnitude of this operation. By July 1940, the CRO was returning hundreds of aircraft to the line every week. Statistical analysis of the RAF's order of battle shows that roughly 35% of the aircraft issued to squadrons during the height of the fighting were not factory new, but category repairs returned to service. Furthermore, we must analyze the specific platforms involved. The Hawker Hurricane, which bore the brunt of the fighting, was structurally primitive compared to the German Messerschmitt Bf 109. It was built of wood, fabric, and a tubular metal framework, utilizing 1,930 seconds technology. While this made it slower, it was a logistical dream. It absorbed damage that would snap a modern stressed skin airframe, and it could be repaired by mechanics with basic skills, often right on the airfield. The more advanced Spitfire was harder to fix, but by keeping the mix of high-tech and low-tech aircraft, the RAF balanced performance with sustainability. The German system had no equivalent to the CRO. A damaged Bf 109 over England was a total loss. Even a damaged Bf 109 that limped back to France often had to be shipped by rail all the way back to factories in Germany for major repairs, removing it from the order of battle for weeks. In conclusion, the industrial miracle was not just about building more planes, though Britain did actually outproduce Germany by a margin of 2-1 during the battle. It was about closing the loop. The British system treated aircraft as a renewable resource. They shortened the supply chain to the distance between a crash site and the nearest garage, effectively doubling the efficiency of their fleet. The Luftwaffe was fighting a linear war of consumption, while the RAF was fighting a circular war of regeneration. Section 4. If Section 3 revealed an industrial triumph, Section 4 exposes a catastrophic human failure. By late August 1940, the logistical reality of the Battle of Britain had shifted drastically. The stock and flow diagrams on Dowding's desk told a terrifying story. The Royal Air Force was not running out of planes. It was running out of people. When we perform a systems autopsy on the RAF, during this critical window, specifically from August 24th to September 6th, we identify the single greatest vulnerability in the British defense: the human bottleneck. In logistical terms, the disparity lay in production lead time. As we have seen, the civilian repair organization and the factories could manufacture or repair a Spitfire in a matter of days. The metal was elastic. However, the lead time to produce a combat-ready fighter pilot was measured in months. In 1940, the minimum standard for a pilot was roughly 150 hours of flight time, culminating in specialized instruction at an operational training unit, OTU. This biological supply chain was rigid. It could not be surged overnight without catastrophic consequences. During the peak of the Luftwaffe's assault on the airfields, the attrition rate became mathematically unsustainable. The data is stark. In just 2 weeks of intense combat, Fighter Command lost 295 fighters and 103 pilots killed, with another 128 seriously wounded. That is a total loss of 231 experienced airmen. In that same period, the OTUs, the factories for pilots, could only output roughly 140 fresh replacements. The system was running a deficit of nearly 100 pilots every 2 weeks. If we project that trend line forward, the RAF would have effectively ceased to exist as a cohesive fighting force within 3 weeks, regardless of how many Spitfires were sitting on the tarmac. This shortage forced Fighter Command to violate its own safety protocols. To meet the frantic demand from the squadrons, the training pipeline was compressed. The OTU courses were slashed from 4 weeks to 2 weeks. New pilots were arriving at frontline squadrons with as little as 10 hours of flight time in a modern monoplane, and often with no gunnery training whatsoever. We see here a classic degradation of quality in favor of quantity, a dilution of the pilot pool. These green pilots were statistically likely to be shot down on their first or second sortie, creating a feedback loop of waste. The system spent resources training a pilot who was destroyed before he could provide a return on that investment. Furthermore, we must analyze the condition of the surviving inventory. The pilots who remained were suffering from extreme operational exhaustion. The sortie rate, the number of missions flown per day, spiked to 3, 4, or even 5. Logistically, a human operator has a maximum duty cycle. Beyond a certain threshold, reaction times degrade, situational awareness collapses, and the pilot becomes a liability. By early September, squadron commanders were reporting that their men were falling asleep between sorties, too exhausted to eat. The human maintenance schedule had broken down. Simultaneously, the Luftwaffe shifted its targeting strategy to focus on the sector stations, the physical nodes of the Doubting system. Airfields like Biggin Hill and Kenley were hammered repeatedly. These attacks were not just destroying hangars. They were severing the landlines and destroying the operations rooms. This was a direct attack on the system's bandwidth. If the sector stations went offline, the information loop we analyzed in Section 2 would be severed. The squadrons would be blind. By the first week of September, the RAF was on the ropes. The intricate system of rotation, where exhausted squadrons in the south were swapped with fresh ones from the north, was jamming up. There were no fresh squadrons left. The reserve of experienced leaders, the squadron leaders and flight lieutenants who held the formations together, was critically depleted. This is the moment where the German systems analysis failed them. German intelligence, suffering from a chronic inability to accurately assess bomb damage, BDA, believed the RAF was already finished. They overestimated British losses by a factor of 3. On September 7th, acting on this flawed data and political pressure, the Luftwaffe made a fateful decision to switch their main effort away from the airfields and onto the City of London. From a strategic narrative perspective, the blitz on London was a tragedy, but from a purely logistical perspective, it was the miracle Doubting needed. When the bombers turned toward the city, the pressure on the sector stations instantly evaporated. The cratered runways were repaired. The severed landlines were reconnected. Most importantly, the pilot attrition rate stabilized. The target-rich environment moved away from the fragile logistical hubs of the RAF and into a massive urban center that, while suffering human tragedy, could absorb the punishment without losing operational capability. The shift also changed the tactical geometry. When attacking the airfields, German fighters were right on top of the RAF as they took off a counter-air strategy that caught British planes at their most vulnerable, low-energy, climbing. When the Germans attacked London, they had to fly deeper inland. This gave the British squadrons more time to assemble, climb to altitude, and engage the enemy on favorable terms. The system's autopsy of this phase concludes that the RAF did not win this specific attrition phase. They survived it because the enemy disengaged from the critical bottleneck right before it snapped. The Luftwaffe failed to recognize that the center of gravity was not the city, nor the morale of the people, but the delicate, exhausted supply chain of the Pilot Training Command. By shifting targets, they allowed the RAF's human system to reboot. Section 5. On the 15th of September, 1940, now celebrated as Battle of Britain Day, the Luftwaffe launched massive, coordinated raids against London, expecting to deliver the coup de grace to a shattered enemy. Based on their data, the RAF should have been incapable of putting up significant resistance. Instead, German bomber crews looked out their windows to see the sky filled with hurricanes and Spitfires. The psychological shock was absolute. The German High Command had to face the reality that their model of the enemy system was fundamentally flawed. 2 days later, Hitler postponed Operation Sea Lion indefinitely. When we deliver the verdict on this campaign, we must move beyond the romanticism of the David versus Goliath narrative. The RAF did not win because they were lucky. They won because they operated a superior logistical system. The German defeat was a failure of intelligence feedback loops. The Luftwaffe commanded a massive industrial output, but they lacked the sensory organs to know where to apply it. They fought blindly, shifting targets based on poor data, failing to identify that the true center of gravity was the sector stations and the pilot training pipeline. They treated the battle as a linear accumulation of kills, assuming that if they shot down enough planes, victory was inevitable. In contrast, the British victory was a triumph of systems integration. Doubting, Park, and Beaverbrook understood that air power is not a noun. It is a verb. It is a flow. By integrating radar, detection, the observer corps, verification, the filter room, processing, and the civilian repair organization, regeneration, they created a closed-loop system. This allowed them to achieve local superiority at the point of attack, despite being numerically inferior overall. They maximized the utility of every gallon of fuel and every pilot hour. The ultimate takeaway from this autopsy concerns the valuation of assets. The Luftwaffe focused on destroying hardware, the airframes. The RAF focused on preserving capability, the pilots, and the infrastructure. The human bottleneck we analyzed in Section 4 proves that in high-technology systems, the most critical component is often the most fragile and the hardest to replace: the human operator. While the factories could surge production of metal wings and Rolls-Royce engines, the human mind takes months to train. The system nearly collapsed not because of a lack of machines, but because it burned through its expertise too quickly. The lesson for modern logistics and operations is clear. Resiliency does not come from hoarding inventory. It comes from protecting the throughput of your most constrained resource. The RAF survived because they built a safety net radar and rescue around their scarcest asset, allowing them to regenerate combat power faster than the enemy could destroy it. To look back at the summer of 1940 is to see more than a military victory. It is to witness the birth of modern systems thinking. The Spitfire remains the icon, but the true hero was the invisible architecture that kept it flying. The lesson echoes through every modern supply chain. Survival depends not on the size of your stockpile, but on the resilience of your connections and the protection of your people.